you'll look at your homework, look at number 35.
So number 35, it says from 1997 to 2002, the number n in millions of DVDs players sold can be modeled by the equation n equals 0.42 times 2.47 to the power of t, when t is the number of years since 1997. And part A tells you to find the initial amount, the growth factor, and the percent increase. So comparing the original equation to the exponential growth equation, you see A corresponds with 0.42, which means the initial amount would be 0.42 million, and 2.47 corresponds with 1 plus r, so you set that up as an equation and subtracting 1, you get 1.47, which equals 147%, and the growth factor is just what you get in the parentheses, which would be 2.47. And for part B, you have to find the number of DVD players sold in 2001. So you just plug 4 in for t, and 2.47 to the power of 4 would equal about 37.22, and multiplying that by 0.42, you get 15.6, so that means 15.6 million DVD players were sold in 2001.
So just kind of reiterating, awesome job, Connor. Like the difference between what everything means. So the number of friend is the initial amount. The problem was given in millions. So make sure that you're labeling that. That's just not 0.42, it's 0.42 million. You could write that as well. It's 420,000 if you wanted to instead of 0.42 million. The number inside here is the growth factor. So that whole number inside the parentheses is the growth factor, but that rate or percentage would be, as he has here, like that 1 plus r is equal to the 2.47. So the rate and the growth factor are different from each other. So the growth factor is 2.47, but the actual percentage rate that it's growing by is 147%, which is huge. Usually we're talking about like a 3% growth. This thing is growing by 147%, and you get that by pretty much setting this, subtracting 1 from that value. So he has that 1 plus the r equals 2.47. Awesome job. Really good. Questions for 35? So Melanie has 37. Yeah. And 37 kind of gave you an example with the compound interest formula.
Okay, so for the first one, the 0.03 comes from the 3% that the annual interest is compounded, and your like initial equation that you're like working off of is 2,200 times 1 plus r over n times 4n. And so the 0.03 comes from the 3% for letter A. And then when it says quarterly, that means you multiply the exponent 4 by 4. And then when you do the multiplication, you get $2,479.38. And then for the next one, 2.25% as a decimal is 0.0225, and then because it's monthly, you divide it by 12, and then you also multiply the 4 by 12, and then you get $2,406.95. And then for the last one, 2% is written as 0.02, and because it's as daily, you divide it by 365, and then you multiply the 4 by 365, and then you get $2,383.23.
Nice explanation. Any questions on 37? So you can kind of see like the difference in those amounts as the number of times compounded increases. or decreases depending on the way you're looking at it there. Nice job.
Thank you.
So, we're going to do just a handful of notes today. We're going to look at a couple of graphs in section 7.2, and then I have an activity that you're going to do that involves exponential growth and decay. And I'm going to show you a little trick to kind of graphing, a shortcut to graphing, so that you're not getting all those crazy decimal values and, or I should say fractional values. So it'll help eliminate some of those crazy fractions when you're graphing. Also help eliminating the force of using the calculator. So if you can take out section 7.2, we're just going to do a handful of notes. We're going to look at like 2 graphs. And then as I said, I've got an activity for us to look at. This is 39 for A. So there are 2 different types of graphs. It can either grow, which means it's going to increase, or it can decay, which means it'll decrease or go down. Yesterday we looked at the growth ones where they started low and then they curved up high. So today we're going to look at the graphs that go down and decay. And then tomorrow we'll kind of look at some word problems and try and pull all the different types of word problems together that you can have. So exponential decay function still is the same. There we go. Equation. So we still have that equation y equals ab to the x. So the equation isn't changing. The a value is still a positive number. That's not changing. So should say, how about greater than 0, not greater than 1? Positive means bigger than 0. It could be a fraction. But the b part is the part that's going to change. So for it to grow, b has to be larger than 1. So for this to grow, it has to be larger than 1. For it to decay, what do you think has to happen with the b value? If it's going to decay or go down. So if it grows, it has to be bigger than 1. Julian, what do you think would have to happen for it to decay? It has to be less than 1, but also greater than 0. We're not going to have a negative b value. So it's going to be less than 1. I'm going to put another inequality on the other side, but greater than 0. So a has to be positive because that's our initial amount. And an initial amount is a positive value, especially when we're talking about real life things. So you have an initial amount of money, you have an initial amount of animals. We did the buffalo problem yesterday, but you've got an initial amount of something. The b part, if it's between 0 and 1, it forces the graph to go down. If it's above 1, then that's how it grows and it goes up. So if it's a fraction, your graph is actually going to go down. Where if it's a large whole number, the graph goes up. The decay factor is still b. Again, it's decaying now because of what that b value is. So it can be a growth factor, it can be a decay factor. It has both terms, it just depends on what the actual value is. So as I said, today we're just going to look at the graph part. There's that parent function that's underneath. So in this function, we have that y equals b to the x, which we saw yesterday as well. Except this b value is between 0 and 1, so that you can see the shape of the graph, the fact that it falls So it's starting up high, but then it's going down. It still has this part at the bottom that kind of just like curves, or not really curves, but kind of levels off. So this piece right here, there we go. It kind of just levels off. And in your graphs, make sure that you extend it. Don't stop at the last point or the first point that you chose, the last point that you chose. Make sure you extend it to show that it actually is leveling off. Because it doesn't go below the x-axis unless the graph is actually shifting down or shifting up. But you should kind of have it that it's just kind of horizontally leveling off after that. Those points get really close to 0. So the domain of this graph is the same as the domain of the growth graph, and that'll be the same for every single exponential function. And that's because you can put in any number for x. It doesn't matter if it's negative or positive, a whole number or a fraction. An exponent can be any value. There's no restrictions on that. But the range is the part where there is a restriction, because if you look at the graph, it's only drawn on a portion of it. It doesn't go through the whole graph, or the whole kind of axis that we have here. So what would the range be of this graph? Emma, what would the range be?
0
Yeah, it's the same range as the growth graph. So it's not going to touch 0, it's going to get really, really, really close to 0. And that's because an exponential function, because you have a base, a number with a power, there's no way that base can become 0. So it gets just really, really close to it. So the domain and the range, whether it's growing or decaying, is the same domain and the range. So the domain stays the same every single time. So if you look at the first graph, we're going to graph this one, and then we're going to flip it, and I want to kind of show you how we can try and look at a graph and use this information and avoid getting those evil fractions that you had in some of those problems yesterday. So this one says graph the decay function, determine the domain and range. Most of your homework tonight is graphing. So I'll give you a graph when we're done, but I think like 6 of the problems are graphing again. So we have y equals 2 to the 1/4 x. Make yourself a little t-chart. If you start to freeze, let me know. I just tried to turn that thing down. It feels like it's pulling out a whole bunch of hot air. So, same numbers that we chose yesterday. Gonna try and not rely on the calculator and do some mental math. So, the first number we're plugging in is -2. So we have 1/4 to the -2. What happens to the 1/4 when you take it to a negative exponent? Julia?
You have to flip the numerator and denominator.
Yeah, so this flips. So when we had 4 to the -2, the 4 went to the denominator. Well, now that it's in fraction form and it's to the -2, that denominator is going to go up to the numerator. So this is really taking 2 times 4 squared. So the negative exponent takes a fraction and actually makes it flips, or in this case, it makes it a whole number. So we're looking at 2 times 16, which is 32. So no calculator necessary. I want you to think of those properties of exponents that we spent all chapter doing, chapter 6. So the next one is 2 and then 1/4 to the -1, which is really just 2 times 4. So you can see that my first number started out pretty large at 32. The second number dropped to 8 already. And then just continuing it, 2 times 1/4 to the 0 is really 2 times 1, which is just 2. And then we have 2 times 1/4 to the 1. So 2 times 1/4 is 1/2. And the last one, 2 times 1/4 squared, which would be 2 times 1/16. Again, don't pull out that calculator. Square the top, square the bottom. So 1 squared is 1, 4 squared is 16. So that's 2/16 or 1/8. So all those powers that we are working on, kind of just focusing on those powers but applying them to a graph of an exponent. So the first one at -2, we have 32. Obviously, we can't really graph that. We know it's way high up off the graph. But at -1, We can definitely graph that. It's 1 off the graph. At 0, we're up at 2, and then we have a half and an eighth, and that's when it starts getting smaller. Those numbers are gradually going to get smaller once they get closer to 0. So it's a drastic increase at first, but then it's a gradual or really small increase. So when you connect them, try and make that bottom part curve to connect the dots, but then extend it beyond your points. So it does have that point where it's leveling off, where it's getting closer and closer to 0. So, Garrett, what would the domain be? And the range?
0 to infinity.
So I'm not going to graph the next one because I want to graph one that actually has a little shifting to it to show you how we're going to graph those shifts. A little shortcut instead of using all those evil fractions. So if you flip the page, so pretty much the same stuff, but now the graph goes down instead of going up. So on this next page, again it says graph the following functions. The only difference with this function is that we start to have some movement. We've got that x minus 1 and the plus 1. Can anybody just describe how this graph should move? So how's this graph going to shift with that minus 1 and the plus 1? Melanie?
Up one, right one.
Yeah, so this part here makes it go up. That part here, you're taking the opposite. That makes it go right. So up 1 and right 1. So instead of graphing it with those extra numbers added to it, we're going to try and see if we can make a short way around graphing. And I'm going to take those extra numbers out of the problem. So instead, we're going to keep the 2, keep the 3/5, but just place an x with that. So I'm ignoring the plus 1, the minus 1, actually the minus 1 and then the plus 1 for right now. So I'm going to show you another way that we can graph using that information in a minute. So make yourself a T-chart. We're going to graph this more basic function here. And that's just like the one we just graphed. So a little more basic. Now, yeah, I know we've got a 3/5 in here. So you might need to put a little scratch work on the side. So we have 2 and then 3/5 to the negative 2. So Julia, what did you say what happened when you had a fraction with a negative exponent?
You flip the numerator and denominator.
So this becomes 5/3 squared. Julia, I'm going to pick on you one more time. What happens when you have a fraction and it's squared?
You square both the top and the bottom.
So this becomes 25/9. And when you double that, Julia, what do you get?
50 different things.
Very good. So square the top, square the bottom. Not using a calculator here, just squaring pieces of the fraction. 2 means you're doubling that number. So 2 times 25 is 50. The bottom just stays as 9 because it's 2 over 1. So that's 50/9. All right, so doing the same thing with negative 1. Again, if you need to put a little scratch work, you're going to have a portion of the test and the quiz again be a no calculator portion. So doing a little bit of scratch up on the side if necessary. We're taking 2 and then flipping it 5/3 now to the positive 1. So we're doubling 5/3, which means it's now 10/3. The next one, we have 3/5 to the 0. Well, 3/5 to the 0 is 1, times 2 is 2. And then we have 3/5 to the first. So we're doubling the numerator, making it 6/5. Odette, you okay over there? You're not freezing yet? And then the last one, we're taking 3/5 and squaring it. So squaring the top is 9/25, and then doubling it to get 18/25. A lot of good fraction work there. So we're going to graph these points. We're still not doing anything with the extra -1 and +1. So we're going to graph these. So at -2, we have 50 fourths. Well, I know 9 goes into 45 5 times, so that's going to be a little more than 5. So negative 2. It's about 5 and a half. And negative 1, 10 thirds is 3 and a third. So negative 1 up 3 and a little more. At 0, we're at 2. 1 and 6 fifths. 6 fifths is a little more than 1. 18 25ths is a little more than a half. That's something wrong with that last number? 9 25ths to 18. Like, anybody get something different here? It should be bigger than 1. No? Oh, we didn't get that one yet. Never mind. My fault. Okay. So let's graph it. I'm like thinking one step ahead. Connect those points. And then the last thing, we are going to now just shift the actual graph. So we're going to actually do translating on the graph instead of translating in the t-chart. So with your first point, which is the one over here, actually let's start up here. We're going to shift it right, so move it right and up 1. So now we're doing graph shifting, which is something you did a good bit last year in geometry. You translated those shapes. So we're shifting these points using the right 1 and up 1 fact. So here we're going right 1 and up 1. Right 1 and up 1. Right 1 and up 1. There's my point that I was thinking about. And now, yes, we have 2 graphs, but we didn't need to use a calculator, even though I'm sure you wanted to. But we didn't have to use a calculator. We were able to kind of translate the graph off of a more basic graph. So that's graph translating, using the fact that it's moving right and up, and actually applying that to the points. So the domain would be from 0, about infinity, to infinity. And then this time the range, because it's shifted up 1, that range now starts at the place where it's shifting up or down. So anytime a graph shifts, it moves up or down. That's what affects the range. So the range starts at 1 now, and it goes to positive infinity. So that value, that's our k value, that's going to affect the range still in these graphs and the graphs that you drew before. Questions? So I have an activity. I'm hoping 15 minutes is going to be enough time. It deals with Skittles, so you're going to kind of work with Skittles. I do need you to get a partner because I only have so many bags. I've got 13 bags of Skittles. So I need you to get a partner. Even if you don't know anybody in class, just partner up with somebody next to you. I'm going to give you Skittles. You'll have to count them. I'm pretty sure there's about 50 in them. Connor, did you get one? So grab a partner, kind of look at the directions. The first part is pretty easy. You're going to just be kind of flipping Skittles. Well, wait, I'm giving you all.
Like I was going to bed early.
Take these away. Thank you. And then oh, we have one. Got it.
I think the letter side is.
Anybody not get a bag? You and your partner need to get a bag.
I'll make letters.
So now to make sure that you have 50, you need 50. That's what I would suggest starting with. Put them in your cup and Don't put it back in. So again, make sure it has an S on it. Did I count right for you guys?
This one has a big dot on
You're gonna put them all in the cup then, and just read the directions, see what you're doing.